Hi, today is Saturday, January 7th, 2022. I am sitting in front of a space heater and I'm trying to read this article to warm myself up. And before I hit the sack, I would like to read one more article. The reason I am trying to read this article is to learn about new technology, new concept, creative ideas, and so on, while practicing English by reading it carefully with correct pronunciation and with a focus on picking up good words, phrases to remember. So here we go. It's a multiple purpose effort. So here we go. Interesting engineering. What Einstein meant by time is an illusion. When you think about it, time is an arbitrary construct. It's our way of making sense of growing up and growing old. By Jamie Trasper, July 27th, 2021, 5-minute read. I think it will be like a 17-minute read for me. Yeah, that's a good concept. Time is just conceptual. It's not a firm, definitive, set in stone rule that is applied all over the universe. It's just a concept by humans. There are all sorts of quotes about time. One of my favorite quotes is by Ajit Naskar, the author of Love, God, and Neurons, memoir of a scientist who found himself by getting lost. He said time is basically an illusion created by the mind to aid in our sense of temporal presence in the vast ocean of space. Temporal presence, that's good. Time, temporal presence. Without the neurons to create a virtual perception of the past and the future based on all our experiences, there is no actual existence for the past and the future. All that there is the present. One of the most influential physicists to have ever lived, Albert Einstein, shared this view, writing, people like us who believe in physics know that the distinction between past, present, and future is only a stubbornly persistent illusion. In other words, time is an illusion. When you think about it, it makes sense that time is an arbitrary construct. It's our way of making sense of growing up and growing old while the world changes around us. It's not all that hokey. So let's look at how our perception of time changes in different locations. I forgot the meaning of the hokey. I knew the meaning before. It's not simple, I think. Hokey means it's not simple. Hokey is excessively sentimental, fake, artificial, contrived. Hokey means corny, mawkishly sentimental, or obviously contrived. Hokey can also refer to hokey or hokeyist, excessively sentimental, fake, artificial, contrived. Let's go back. It's not all that hokey. So let's look at how our perception of time changes in different locations. It's all relative. According to Einstein's own theories, time moves differently for someone below sea level than for someone situated on the highest peaks on the planet. According to some studies, at sea level you age 1/billionth of a second less every year than you would if you lived on top of Mount Everest. This is due to a phenomenon posited by general relativity called gravitational time dilation. The logic behind gravitational time dilation is fairly simple. Objects with a lot of mass create a strong gravitational field. This gravitational field noticeably warps the fabric of space-time around these objects, producing what we know as gravity. When a stream of light particles passes by an object with sufficient gravity, the stream of photons traveling at the speed of light would appear to bend. What's even more interesting is that mass can warp the very fabric of time itself. Causing it to move slower or faster depending on how massive the object is and how strong the object's gravitational pull is, which is where time dilation really becomes wonky to us. An astronaut venturing into a black hole, source NASA, astronaut, NASA, ESA, and G. Bacon, STSCL, black hole illustration. It should be noted, however, that an observer in the strong gravity experiences time as running normally. It is only in relation to a reference frame with weaker gravity that time runs slowly. To a person in strong gravity, time appears to pass normally, while a clock in weak gravity runs fast. While to the person in weak gravity, the clock appears to run normally, the clock in strong gravity runs slowly. Of course, there's nothing wrong with the clocks. Time itself is slowing down and speeding up because of the relativistic way in which mass warps space and time. The faster one moves, the slower time passes in relation to a static observer's perception. Matter traveling at the speed of light does not really experience time or distance, at least relative to a static point. Just watching a spaceship drift off into deep space, the people on Earth view the ship as moving much more slowly through space and time than the people on the ship perceive it to be moving. Crew members would also age at a slower rate the faster they move, making time dilation easy. Take another cool example, the movie Interstellar, in which time dilation is demonstrated. Spoilers beyond, obviously. In the movie, a crew leaves Earth in search of a habitable planet we could flee a dying Earth for. At one point in the film, a few crew members land on a water world located not too far from a gargantuan black hole or wormhole. Given their proximity to the super-dense stellar object, the planet experiences unimaginably volatile waves, and the time dilation becomes extreme. 1 hour on the surface was equal to 7 years for someone beyond the black hole's orbit. Astronauts on the ISS experience a much less dramatic form of time dilation, given the International Space Station is not traveling anywhere near relativistic speeds. 2 twin astronauts were part of an experiment conducted by NASA. They calculated that the twin who spent the most time in space actually aged 5 milliseconds more than his earthbound twin. It gets even weirder. Perhaps the strangest example of time dilation can be seen in and around black holes. Time ticks much differently the closer you get to the event horizon of a black hole. Imagine that you had 2 clocks, one held by an observer beyond the immensely strong gravity of the object, and another held by an observer
passing near the event horizon. The clock farther away would tick faster than the one close to the event horizon. From the point of view of the observer near the event horizon, 1 day may have passed, while the person observing from the outside may have experienced a decade of time. Eventually, time may appear to stop altogether for the observer near the event horizon. From the outside, the observer at the event horizon would begin to redshift, which means the wavelength of light they emit would move toward the red portion of the electromagnetic spectrum until the light becomes dimmer and dimmer. Inevitably, time would appear to stop altogether before the observer plunges into the event horizon. In theory, we would never actually see this occur, as the object would appear to freeze and never actually disappear from sight into the black hole. Black holes can be formed when a massive star reaches the end of its life. Its core begins to collapse in on itself, spitting out large quantities of gas and dust in the supernova event. Gas and dust in a supernova event. The star must be at least 3 times as massive as our sun in order for this process to occur. It is thought that supermassive black holes, which range from 100,000 of times of the mass of the sun, from 1 billion of times the mass of the sun, may be formed by a sort of chain reaction, and this is where extreme time dilation comes in. Devoured by a big old black hole. If you are wondering what actually happens when something finally gets sucked into the event horizon, the point at which nothing, not even photons or light itself, can travel faster than the object's escape velocity, thus there's no chance of escaping its grasp, the physics gets rather convoluted and our understanding of how things work begins to fall apart. It is believed that an observer inside a black hole would eventually stop experiencing time altogether, but they would become stretched out as the black hole slowly ripped them apart, atom by atom. This is called spaghettification. The forces of gravity during a so-called tidal disruption event would pull harder on your head versus your feet, and you would be shredded. Artist rendering of star undergoing spaghettification as it's devoured by a supermassive black hole during a so-called tidal disruption event. Source: ESO K.M. Comesser. Thankfully, we can sometimes measure these events, at least when they happen to our stellar objects. This is because they produce a lot of energy we can detect using specialized telescopes like the ESO. Often gas and dust obscure our view, but if we catch an event at the right time, we can study just what happens when matter is devoured by a supermassive black hole. As for Einstein, as we saw from Einstein's quote, he believed that time is an illusion, that both the future and the past are unchangeable and will play out exactly the way they were meant to. Many physicists share this view, but there are some that have alternate explanations for the way things will play out in the long run. One suggests that the present, future, and past are still mostly unwritten, or they are all playing out at the exact same time. The black universe theory contributes a lot to these ideals. Overall, do you think Einstein was right or wrong? I don't know. Thanks for listening. It's a little bit esoteric. So one thing is clear. When we move faster, we age more. When we move slower, we age less. So, and when we are near a black hole, we age less compared to someone outside the influence of the black hole. And when we are inside the black hole, we would experience redshift, and our body will fall apart atom by atom, and the supernova exudes dust and what else? Dust and gas when it collapses on itself. Thanks for listening.